All right, great. Welcome everyone to today's project presentation. So this is going to be a series following the summer school where we had a lot of alumni with great projects that we can actually dig into a little bit and do a bit of a deep dive into some of the actual insights and interesting things that they were able to achieve. So today we're joined by Fergus Noble, and he's going to be doing a project involving gravity and hypergraph rewriting, and Nick and Dugan are also in attendance. So with that, Fergus, I'd like to hand it over to you and you can tell us what it's all about.
Great. Here, let me go ahead and share my screen. Okay, is that coming through?
Yep, looks good.
Yeah.
Yep, looks good.
All right. So yeah, today I wanted to walk through my project for the Wolfram Summer School that just concluded a couple of weeks ago. And it's around searching for rules that preserve geometric structure in Wolfram models. So I'll talk a little bit more about what that means. But first, I can just introduce myself. So my background was originally in physics, although I'm very much a lapsed physicist. I got my master's in physics back in 2011 from the University of Cambridge. And it was always my intention to stay in physics, but I ended up taking a little bit of a 90-degree turn and had the opportunity to start a company called Swift Navigation. We were working on localization for autonomous vehicles, and that's really what I've been doing for the last kind of decade plus. I would say there was maybe some physics adjacent aspects to that. We were working to improve GPS accuracy through atmospheric modeling, but as that wrapped up, I really wanted to reconnect with my physics background and had the opportunity to participate in the Wolfram Summer School, which is an awesome program hosted by Wolfram. It's a 4-week program just outside of Boston. And one of the things that was really cool about it is there's huge diversity of different students and different topics, but I was in the track focusing on the Wolfram Physics project, which I'll talk a little bit more about what that's all about. So I imagine a lot of people dialing in already are quite familiar with Wolfram models, but just in case anybody is not, then I'll just very briefly introduce, what is a Wolfram model, and then I'll talk about my specific project. So at its core, the Wolfram model is a pretty simple concept. So in a Wolfram model, you have really two things as a starting point. You have a graph or a hypergraph. I'll say a little bit more about what a hypergraph is, but for now you can just think about simple graph consisting of vertices and edges, and then you pair that with a rewriting rule. So rewriting rule, you take a subgraph that matches the left-hand side and you replace it with the graph on the right-hand side, and you can repeatedly apply this rewriting rule. And so it turns out if you use this idea of rewriting rules on graphs, it can start very simple, but very quickly you get a lot of very interesting, very complex emergent behavior out of these graphs. So on the right-hand side here, you can see we start with just like, the simplest graph that could possibly match this rule with 3 vertices and 2 edges. And just through repeatedly applying that rewriting rule, you can end up with very complex kind of emergent behavior coming out. So, if you keep applying it for a bunch of different updates, you can get some pretty interesting results. And with different rules, you get, just a very wide diversity of different kinds of behaviors. I'm not going to talk too much about hypergraphs. In my project, I didn't, I focused on kind of more simple graphs, but I think, any discussion of the Wolfram model, goes hand in hand with hypergraphs. So hypergraph is a kind of extension to the idea of a graph where, in a graph you have edges that connect between 2 vertices. In a hypergraph, you extend that to the idea of a hyperedge that can potentially connect between multiple vertices. So the hypergraph on the left you can think of as, having 2 hyperedges, the first one connecting vertices 1, 2, 3, and it can be directed. And the second hyperedge connecting vertices 3, 4, 5. And just as in the case we showed before, you can have rewriting rules on hypergraphs as well. And, I think why hypergraphs? Well, with a hypergraph compared to a simple graph, you get they can be a lot more expressive. There's just a lot more different ways you can kind of connect vertices that can result in even more kind of rich and complex behavior. But in this project, I'm just going to focus on the simple graphs, and I'll talk a little bit about why that is. A couple more slides. Okay, so what does any of this have to do with physics? So, we're starting with a simple idea of graphs and rewriting rules. And it turns out, these systems can have a lot of parallels with physical behavior. So one of the kind of first things you see is a lot of different rewriting rules, starting from a kind of minimal initial condition, like a single vertex. Will grow these structures that seem to have these kind of geometric properties, right? So on the left, you're getting a kind of grid-like structure with, which looks like a kind of two-dimensional surface. In the middle, a different kind of two-dimensional surface that has some curvature, and then on the right, again, the third type of two-dimensional surface with even more kind of complex geometry to it. So you can kind of imagine, if you keep applying these rewriting rules for long enough, then you might, in some kind of limit, get the notion of a kind of continuous space. And so others have actually built a lot of the tools of differential geometry on top of this. So there've been kind of well-defined notions of dimension, curvature, and so on. Just in terms of the graph structure. So kind of one of the things you've got to keep in mind is to throw out, obviously to display these graphs, they're embedded in the 2D space on the screen. You've got to throw that, kind of keep that out of your mind and just think in terms of the actual, structure of the graph itself. And from that, you can build a lot of the tools of differential geometry. But I think one of the things that really kind of caught my attention when I first started learning about this is that, not only can you build differential geometry, but there is actually pretty broad classes of rules that will cause that manifold structure that results from the graph, from the rewriting rule, to evolve according to the Einstein equations. And it's a pretty broad class of rules. There's some just fairly minimal assumptions you need to make to be able to show this behavior. So you need the rule to kind of asymptotically preserve dimension. And there's a kind of ergodicity requirement in there as well, saying that the rule's got to act, across the whole graph. And really, you don't need too much more than that to be able to recover something, analogous to the Einstein-Hilbert action and be able to recover the Einstein equations as a kind of continuum limit of rewriting systems.
That's great. Can you define ergodicity for us just momentarily there, please?
Yeah, I don't know if I can give you kind of like a very technical definition in this case. There's actually the link at the bottom there for anybody who wants to dive into all the gory details. But essentially it means that, you don't want the rewriting rule to kind of only apply in certain areas of the graph. It's got to kind of, on average, that rewriting rule is going to kind of visit all the different areas of the graph, essentially. Yeah.
Got it.
So it's not kind of acting in a biased way. And so, from this, there's a lot that's been built, in terms of these parallels to relativity, including even some frameworks that have been used to do numerical relativity simulations. So here's some really, really cool plots that were generated. And again, the paper is down below, just from earlier this year, showing simulation of black hole mergers using these kind of graph structures. So I think it was really remarkable to me that starting from such a simple starting point, you can actually start to recover so much correspondence with physical theories.
Yeah.
So I'm going to focus really on the kind of relativistic aspects in this presentation, but there are tons of other kind of avenues that have been explored. One is that there's not a unique way to apply the rewriting rule in general on a larger graph. So you can start to build some mechanisms that correspond to some quantum mechanical behavior by thinking about, simultaneously applying all the different ways that you can do the rewriting rules. You might ask, well, how do you get kind of, we've got space, but how do we get matter? How do we get particles? And there's been some good work done on that in terms of, are there certain kind of topological features in a graph that will be preserved under the rewriting rule that can give you particle-like behavior? We looked, in the previous slide, we were mostly looking at kind of vacuum solutions, and that's what I'll continue to look at. But there's well-defined kind of notions of matter and energy that can allow you to get, kind of dynamics, and then even some very interesting directions around, can we get a more detailed look at what a quantum measurement process might look like, and potentially even some experimentally testable kind of results. So I just wanted to bring up that, it's not just general relativity. There's a lot of other kind of features of these models that can show very rich kind of correspondence with physics. All right, so specifically onto my project. So my project at the summer school was to conduct a search for different kinds of rewriting rules that are going to have some correspondence to that relativistic kind of behavior. And so, from the previous result, we know that some rules may follow the Einstein equations, but we don't know very much about precisely which rules those are. And so my project was an attempt to do a systematic, really a computational search for rules that potentially could be candidates to be able to model relativistic behavior. And so in order to do this search, we really needed to simplify the problem. And so as I mentioned, kind of the core concept of my project was to look at static vacuum solutions of the Einstein equations, specifically just kind of your regular flat space and also Schwarzschild black hole solutions. And then the idea is that, as a kind of necessary but not sufficient condition, a suitable rule should not change that kind of macroscopic geometric structure of the graph under repeated application, because essentially it's supposed to be a static solution. In the Wolfram model, typically, we talk about starting with some minimal initial condition like a single vertex and then building up the graph from there with the rewriting rule. But it can be difficult to figure out which rewriting rule you need to generate a kind of a given geometry. So, to further simplify the problem in this project, I start by just preparing a pre-prepared kind of initial condition, pre-prepared patch of a graph that has that correct initial geometry. And then what we're going to do is simply kind of go through all the different possible rules, repeatedly apply them, and see how that changes the geometry. So thinking about preparing that initial condition, the first thing that kind of comes up is, it's not uniquely defined. So if you have a certain kind of metric or, large-scale geometric structure that you want to model, there's many possible graphs that have that same kind of continuum limit. So here, pictured, these are all small patches of a graph representing flat two-dimensional space. But you could have, a rectangular grid, you could have hexagonal grids, you could have this kind of random triangular mesh. And then this last one is prepared using a so-called random sprinkling method. So you randomly sprinkle points, and then you connect the edges if the distance between the points is below a certain threshold. And so, you can have that same kind of macro structure, but all of these different in terms of different microstructure. And going back to, some of those initial slides, certain rules tend to build their own microstructure. So it's likely that certain rules may have a kind of preferred microstructure. And so, this is a pretty big challenge for this kind of systematic search, because we know how to enumerate different rules. We don't really know how to enumerate different possible microstructures. And there's an interplay, right? Certain the rule that might work well with one microstructure might not work at all with a different microstructure. So that's something I tried to address by taking a sample of different microstructures and comparing the behavior. So we'll look a little bit more at that. Okay, so the next question is how do we systematically kind of enumerate what all the different possible rules are? And in general, it's a pretty hard problem. But there are some simplifying assumptions we can make that's going to make this a lot more tractable for us. So first of all, really just kind of from these methods that we have for preparing graphs, in the simplest instance, we're just going to get simple directed graphs, not hypergraphs. So for this project, I just took the restriction that we're just going to look at simple directed graphs and not hypergraphs for now. The next property that you can look at is if you think about the rule in terms of it's got some number of edges on the input and some number of edges on the output. If the rule tends to introduce new vertices and new edges every single time it's applied, it's quickly going to lead to exponential growth in the size of that graph. And the way that we define distance, just the kind of, normal physical distance between 2 points on the graph is by the number of edges that you have to traverse to get between those 2 points. That would correspond to kind of non-physical, very rapid expansion of space, right? Because you're going to get essentially an exponential growth. So from that, we can restrict the form of the rules under consideration to those that essentially have the same number of edges on the input and the output. Yeah. And so, then the question is how big do we have to go with then? How many edges do we need to consider? This is, I think there's a lot more work needed in this area, but there is some evidence to suggest that after a certain point, a certain fairly low threshold, you don't see new kind of classes of different behaviors from more and more complex rules. And so some of this is from intuition around cellular automata, and also experiments that have been done on these graph rewriting systems, that it seems like once you get beyond about 4 edges, you're not going to get large kind of new categories of behavior. So that suggests, if we could get up to 4 edges, that would be really nice. The problem with that is that the number of different rules with 4 edges is order of about 10 to the 7 different rules. So that's not very computationally tractable. So for this project, to kind of take that first pass, I restricted the rules to just have 2 or 3 edges. And so if you take that restriction, you end up with about 49,000 rules, which is quite a lot, but it's doable. So, these are definitely fairly restrictive kind of set of assumptions that we're taking to make this tractable. I'll talk a little bit more about some of the extensions, but certainly it would be nice to look at in the future, potentially sampling the space of 4 edges. But for now, we're going to stick with 2 and 3 edge rules.
A quick question on the 2 edges. Why would some be 2 and not all just 3?
It's a fairly, you might be able to say, well, 2 edges, you're just not going to be able to see as complex behavior, but we don't know that for sure. And it's a fairly small number to search. So, it seemed worth including just to see the behavior of the two
so
edge
you're
rules.
doing all 2 edges and all 3 edges.
Yes.
Okay.
Yeah. So there's 562 possible rules. If you take all of the possible combinations of the way that you can construct kind of 2 edges, that results in 562 rules, and then about 48,000 with 3 edges. So it's just systematically enumerating every possible kind of combination of edges that you could have.
Got it.
So it really is an exhaustive search, essentially.
What about like a couple of rules instead, but with small amount of edges, like 2 edges to 2 edges, but 2 rules of those together? It would be like, it would be like comparable number, right, to the 3 edges case.
Seems like that's a good question. So you're saying having 2 edges, 2 rules that maybe kind of applied simultaneously?
Yeah, like both of them can apply. Yeah.
Yes. Yeah. Yeah. So my understanding is, most of the work that's been done has been looking at kind of single rules, but you could definitely extend it to multiple rules. I didn't try to tackle that extension in this project, but yeah, it certainly would be interesting to think about multi-rule systems. I do think there may be some hints that having multiple rules might be important. Maybe can go into to why that might be the case at the end. But for now, just trying to do the simplest thing that could possibly work has been kind of the guiding principle for this project.
Are you putting restrictions on the number of edges? I mean, the number of vertices in the edges?
Not directly, but that will ultimately end up being one of the heuristics that we use to evaluate whether the rule is good or not.
Okay. And the rules you're using, you're saying like in edges to in edges. So you have the input of the rule is a series of edges, and the output is just kind of rearranging those edges amongst the vertices that are input.
Exactly, yes.
And it's not generating any new vertices.
It could generate new vertices. Yeah, I didn't apply that restriction explicitly, but those rules will quickly get weeded out by the other heuristics when we actually come to evaluate, what happens when we apply the rule.
Okay.
Yeah.
Hey, Fergus, can you hear me?
Yes.
Yeah. Sorry, I joined late. As you can see, I'm on the move. Sorry for that, but excited to see this presentation. Sorry, I just jumped in, but I was wondering, so these are symbol-directed graphs, and you're taking any symbol-directed graph into any symbol-directed graph, but you're restricting that the number of edges is the same between the two. Is that right?
Yeah, so we're doing systematic search over all the possible rules that have n edges to n edges for n equals 2 and n equals 3. But on the input, it's a lot harder to enumerate kind of the space of possible graphs. So I did mention, we're going to prepare a patch that has the geometry that we want. So either flat space or Schwarzschild solution. But there's lots of different ways that you could kind of structure the graph that has that same geometry. So in this case, I'll show in a second, we're going to start with these 4 input graphs for flat space, and then we'll do one particular graph for the Schwarzschild black hole.
So I wanted to understand in the, I think, previous slide with the rules. Yeah. So when you have, I don't know where 562 comes from. I'm a bit mystified. Because as far as I understand, there's only one simple directed graph with 2 edges, right?
So this is the possible rules. So you've got to consider the inputs and the outputs, you've just got to count them up.
But I'm slightly confused because simple directed graph with 2 edges, right? There's only one. Sorry, there's 2, right?
Let's wind back a little bit. So the input graph is going to be larger than 2 edges. So there's going to be, we're going to prepare several graphs as a kind of initial condition that could consist of, a couple hundred vertices.
No.
And then we're going to repeat it.
I mean the rule. I mean in the rule, right? Because you're saying your rule is from n edges to n edges, right? And you're saying there are 562 two edges to two edges?
Yeah, I mean there's because it can swap directions, it can introduce new vertices, it can there's quite a lot of things that it can do even with.
Are you allow like loops in the edges? Is it simple?
Yes, I did not explicitly restrict loops, but you'll quickly see anything with a loop on the input doesn't is trivially not going to apply.
And disconnected
to the graphs that we prepared.
Maybe disconnected edges as well.
Yeah, you can end up with disconnected edges. Yeah, there's actually a whole chapter in the physics project technical introduction about how do you enumerate the numbers of rules. So Stephen actually wrote a pretty detailed write-up about how do you count the rules.
Okay, then right. So then simple here means non-multiple, right? Because
simple as in not a hypergraph and no multi-edges. Yes.
Well, right, because often simple also means non-looped, right?
Yeah.
So,
yeah.
But you're saying that
for
loops, right?
I didn't. There may be loops on the rules, but not on the input on the initial condition graph. Does that make sense?
Well, I mean, I don't know if you went over this already, and I'm just very late, but it seems that two-edge simple directed graphs is a very small set and should be fairly transparent where 562 comes from, right? Should be quite easy to just like count it, right, explicitly. And I'm a bit
maybe if I can just continue to the next couple slides, then I think it will show the setup a little bit more clearly, and then maybe you can see if you still have a question.
Sounds good.
Okay, so yeah, if you kind of take my word for it for now that there's 562 rules, and those are the rules, right? And then we also need an initial condition graph that we're going to apply those rules to, right? So, then what we're going to do is keep applying that rule to that initial condition kind of graph, and see how that graph evolves in time. And then we need a set of criteria to kind of, ideally what we're looking for if the rule is going to correspond to, something that obeys the Einstein equations for a static solution, it shouldn't change the geometry of the graph over time. And so that's in general like pretty hard to kind of define really specifically. What does it mean that the geometry should be unchanging over time, over repeated applications of the rule? But we can start with some pretty simple heuristics. And it turns out that this actually gets us surprisingly far using some simple heuristics. A lot of the rules are going to have just very obviously bad behavior. And we're going to be able to filter down our set of rules pretty quickly using just some very simple heuristics. And then in some later slides, we'll start to introduce some additional, more sophisticated criteria as well. But for this first pass, ideally, after repeated application of the rule, we don't want it to just kind of shred the graph into pieces, right? So we don't want any disconnected subgraphs as a result. We talked about how we don't want it to kind of grow exponentially. That would be unphysical. We want the rule to do something. So resulting in a non-zero number of updating events. This kind of goes back a little bit to the question of like, if the rule includes a self loop, that's just not going to match the particular initial conditions that I selected. So that rule is just not going to act. And then we do want to start to get a sense of kind of what does the geometry look like, and the kind of simplest metric of that we can use. We know the number of vertices in the graph is going to stay approximately the same because that was criteria number 2 that we're going to apply. And so a very rough estimate of the dimension of the graph with a roughly fixed number of vertices is we can look at the graph diameter. So the graph diameter is, essentially what is the longest geodesic in the graph. And so if that graph diameter tends to shrink, it will correspond to that graph becoming more densely connected and higher dimension. And so just to give a kind of a sense of, some of the different behaviors that you get, this is just a selection of random rules from that space of 49,000 set of rules applied through 4 generations. So we're going to apply that rule to the graph for 4 kind of complete generations and look at the different resulting behavior. And so these are some that passed after 4 iterations. Some of them are going to fail the criteria on the next iteration because you can see we have some disconnected pieces on some of them. Some of them, there's all kinds of different behavior that you can see here. And then to kind of show how there is that sensitivity to microstructure, on the left, this was the triangular mesh input, and then on the right, this is the hexagonal grid. And you can see pretty different behavior between the 2 different kind of initial conditions. And so for the overall search, and hopefully, Carlos, this will answer your question on what exactly is the setup. So step 1, what I did was do a systematic search on kind of the simplest case that I could think of. And so what we're going to do is we're going to take 4 different initial conditions. So our 4 different initial conditions is these small patches of of graphs that correspond to flat 2-dimensional space, rectangular, hexagonal, and triangular kind of meshes, and then a random sprinkling based graph. So those are our 4 different initial conditions. And for each of those, we're going to go systematically through that space of 49,000 rules and see what happens. So on the right-hand side, what we have plotted here is each pixel in this plot corresponds to one particular rule. So you can see the 2 edge rules here is that much smaller space, and the 3 edge rules, is a much larger space. But it, in the same way, each pixel is going to correspond to kind of what happened after 5 iterations. So if after 5 iterations, all of those heuristics pass, then we'll color that pixel in blue. If, as is the case with, for example, rules containing self loops, for example, they just don't match at all, then there'll be no events, and that pixel will be colored in gray. And if after 5 iterations or less, there's disconnected subgraphs, then we'll color orange. Red corresponds to a greater than 20% increase in the number of vertices from one generation to the next. So those are the kind of the exploding kind of growth conditions. And then there's fewer of them, but you can see there are a couple in pink that have this that fail this criteria, that the graph diameter becomes less than 50% of the original graph diameter. And so, each of these plots corresponds to the 4 different initial conditions. Does that clarify the kind of the setup, Carlos? Does that kind of answer your question?
Are you on mute?
Oh, you're on mute, but I'm seeing nodding. Okay, great.
You're still on mute, Carlos.
Oh, sorry. Sorry, yes. So it does clarify the setup, but it does not answer my question. In the sense that I was trying to understand, and might be worth just reality checking for what we're doing to know what exactly are the sets, because 2-edge simple directed graphs is a very, very small set, right? So I'm thinking if you're allowing for disconnected, then we have two edges that are disconnected, and then you have V, and you have a loop, right? And I think that's it. There's no more.
But it's directed, so each of the edges could go, two different directions, and then you can also permute the vertices. There's the different permutations of vertices, and then also the vertices do not have to be identical on the inputs and outputs.
Okay.
Wait. So
a lot of them are going to be, may result in isomorphic graphs. A lot of the rules may be equivalent, but there are, that's something we'll check for additionally as well.
Okay,
but if you just
that makes sense.
Yeah,
so you're overcounting isomorphic rules, right?
Yeah, there may be isomorphic rules that are double counted, essentially, I believe. Yeah.
I mean, because the ISO class of two edge simple directed graphs has, as we counted, two disconnected, two in the same direction, two in opposite directions, and the V. That's 4 elements, right? There's no more elements in that class, right? And so
you could update to new vertices. So if it's 1, 2, 3, you could have 4, 5, 6. And it's the same.
And that's the same, yeah. But you could also have, there are two edges with 4 vertices, right? Connecting just kind of 2 pairs, right? And then, I don't think I can kind of go through the exact enumeration process here.
We can run it in the code.
Really just, I was just really basing this on the kind of the pre-existing work. This actually, I didn't kind of specifically work on the enumeration process, but as I said, there's a pretty extensive chapter on how to do this in the physics project technical introduction, and they have a procedure there, which is essentially just kind of what I followed, that existing code to enumerate the different possible rules. It's not a perfect enumeration, and I do think that that could be an avenue for further work. We can immediately know that some of these rules are going to result in, for example, no events. We could start by filtering out rules containing self loops, multi-edges, these kinds of things. I didn't do that just because it was a tractable number, and I didn't need to resort to getting too clever. I was just trying to keep it simple. But certainly, if we were tackling the larger space, like the 4-edge space, I think it would pay to be a lot smarter about the way you enumerate the rules.
I mean, that was my angle. I mean, again, it's a matter of actually there are only 3 ISO classes because the two edges in the same direction is non-simple, and you're already ruling out simple in your definition, right? So there's only a V, the 2 disconnected edges, and 2 edges in opposite directions. Those are the only 3 simple 2-edge directed graphs, right? And so how you label your vertices is going to be relevant for the implementation, but it's not going to be relevant for the behavior of the rewrite system, because obviously you're just looking at graphs at the end of the day, right? You're not looking at labeled graphs or named graphs. So my point was I mean, I think this is a really cool idea to try to search for these kinds of things. I mean, I'm totally on board with this, but I mean, it felt like you were overcounting by like an order of magnitude or more in the very beginning.
Yeah, so I mean, that may be that may very well be the case. Yeah.
So Nick, do you know?
So
yeah, sorry, not to get very late, because I have to actually move again in a second. But Nick, do you know about this? How enumeration was happening there? Like,
I think so. I think Fergus just used the enumeration of Wolfram Model rules code, whatever it is, right? I just tried it. How many rules were there exactly? I just tried it. I got like 562 by the end, right?
Yes, it was 562. Yeah.
So I guess I imagine that's So imagine that's taking essentially tuples. So this tuple definition of hypergraphs and actually permuting everything, right? And doing all the combinatorics.
Yeah. So all the loops that are connected, not necessarily connected, I think.
Yeah.
Or rather, it's like the default is right-hand side doesn't have to be connected, but the left-hand side has to be connected to
Has to be.
right-hand side.
Sure.
Yes.
That's correct.
Okay.
Yes.
Okay, but it's a very
Yeah.
brute force edge declaration based enumeration. It's not a sort of graph sensitive enumeration.
No, I think they still filter out all the canonical, all the isomorphic rules. There's no isomorphic rules in that list. So
Really?
but there are loops. Yes, there are still loops and all that in there in that list. So
Okay, there are loops.
Yeah, I believe they've filtered out the isomorphic rules, but there may still be rules that, when acting on the initial condition, result in an isomorphic
Okay.
transformation. Yeah.
I see.
And I
There
think
are-
I started to try to reason a little bit about how you could filter those rules. And I do think it is a little bit, you have to be quite careful how you work that through. And that was just, out of scope for what I was trying to do here. It's just a very kind of crude first attempt, right? And I think, yeah, definitely if you want to search the larger space, you'll need to start getting clever about it.
Okay, no.
Yeah.
Thanks for that. I was not trying to sort of like abstract the presentation. It's just that it seemed like a very high number with a very small set of classes. But yeah, that explains it. And I think it's a great first approach to it. And yeah, excited to see this. Definitely.
Yeah, so this was kind of phase one, was to start again with these very small graphs that all are different kind of microstructures for the same flat two-dimensional space, and see the different behavior under the broader set of rules. And going to much larger graphs than these would be nice. There's a question about, are there kind of boundary effects, right? But this was kind of about the limit of what I could do on one machine with this kind of search space. So we will do this, and then from these kind of full set of exhaustive set of rules, we can look at the passing ones and do some down selection and start to get into some more complex scenarios. But you can immediately see that with the different choices of microstructure, but the same geometry, the same macroscopic geometry, there's definitely some similarities between the density of rules that we get in different regions. Some of that is actually pretty trivial, kind of to Carlos's point. There are whole regions in here that correspond to, for example, self-loops. And so, some of the kind of commonalities in structure is trivial, but some of it, I believe, there's probably a lot to learn about the space of rules from kind of seeing the commonalities here. There's commonality, but there definitely are differences, right? And we do see that sensitivity to microstructure that we were concerned about in the earlier slide. So one of the things you can look at is kind of how much commonality, how much correlation is there between different microstructures. So this is essentially the same kind of plot, but here I've colored in red any rules where all four different input graphs pass the heuristics. And remember, we're only doing 5 iterations also. So, there's a lot that can happen if you were to evolve this longer. In blue, we've got the ones that passed for at least 3 out of 4, and then in gray, any that passed for 1 or 2. And so you can see that, there's pretty good amount of correspondence. So kind of on the larger space of 3 edge rules, we've got about 37% of the rules that pass for at least 1 input pass for all 4. And so for actually, before I move on, I did skip over one slide here. This is just kind of taking a bit more of a zoom in on one of the particular input graphs, the triangular mesh, and you can kind of see a little bit more of the structure in the density plot there. But overall, the takeaway is kind of from this initial first pass, passing rules are relatively rare, but not that rare. So about 2 to 5% the rules kind of pass this first stage criteria. And then, so again, if we kind of apply the additional criteria that we want the rule to pass for at least 3 out of 4 microstructures to move on to the next stage, that filters down our list from 49,000 down to 719 rules. So we're going to take those rules, and then with that smaller set, that's going to free us up to take a little bit more of a detailed look, because we're pretty constrained when we're searching over 50,000 rules. We're pretty constrained on what we can do. It's got to be very computationally efficient evaluation for each rule. So yeah, there's a lot of different kind of choices you could make about what to do for the second pass. I really wanted to try something like a little bit more complex geometry and a little bit of a larger graph. So the next thing I looked at was graphs that correspond to Schwarzschild metric. And so here, very similar setup, but in order to kind of really see some of the structure of that metric, we need more points. So we're going to more than double the number of points in the graph, up to about 500 vertices in this case. We'll come back to this at the end, but unfortunately, one of the limitations of the code that we have to date to construct this initial condition is it is just taking a 2 spatial dimension slice. A nice follow-up would be to do the full kind of 3-dimensional solution. But again, just in the spirit of kind of getting something working in a short period of time, we decided to just continue with looking at this 2 spatial dimension slice of Schwarzschild solution. So that's what you see here on the input graph. This was prepared again by this random sprinkling method. So we kind of randomly sprinkle points according to the metric, and then we connect the points that are sufficiently close. And this is a way of preparing a graph that has that same kind of on a macro scale, has the right kind of geometry that we want to see. And here, this is just plotted with the color is just corresponding to the curvature at that point. And so we take that as an input, and then we're gonna use our down selected set of 719 rules and do the same thing, 5 iterations, of applying those different rewriting rules. And then on the right-hand side here, you can see this is again just kind of a random sample out of those 719 rules, a random sample to see some of the kind of diversity of different behaviors here. And so you see some that look like they might be somewhat plausible. You can still see the hole in the graph corresponding to the event horizon potentially still represented there. And then you see some more pathological behaviors, getting very spiky, getting very densely connected, and so on. And so if we apply the same set of criteria that we had before, we can do the same kind of plot essentially. And as we might expect, because we've already selected these rules for being, for passing on the simpler inputs, we get a much higher percentage passing on this second round. But we are able to start to weed out some of those graphs. So we get a lot, failing the graph diameter criteria, a few disconnected, and then here's where I added in one additional heuristic to check, checking that the after applying the rule is the resulting graph isomorphic to the input graph. So that's a little bit of a different condition than the rule itself being isomorphic, but we do see like a reasonable number of rules are essentially, they do apply and they do update the graph, but they, in some sense, are trivial rules. They're not really changing the graph. Now, it may be the case that in like a non-vacuum solution, or if you have some notion of particles, maybe these isomorphic rules actually do display some dynamics, right? But so we don't necessarily want to totally exclude them, but at least for this case of vacuum solutions, there's not really much further we can go with these kind of trivial rules. So as a result of that, about kind of 3/4 of the rules still pass. But as we said in the beginning, graph diameter is a pretty crude way of looking at, is geometry preserved, right? So, with this project, I was able to just kind of maybe go one half step more kind of in detail around the geometry. And so one of the things that you can start to look at is, the dimension. And I think we're running a little short on time, so I'll just be fairly brief on this. But
you can take as much time as you need for it. So yeah, just
okay.
Get the juicy details out there.
Just one. Yeah. One. Just sorry to interrupt, but I'm gonna have to go because I'm in the middle of a road trip, and you can see I stopped in my car just to see, because I really wanted to get to see this live. I will watch the recording, so I have to say this looks very cool. Thank you so much for this. I look forward to further interaction when we have the chance. And yeah, I'll watch the recording and see you soon, guys.
Cool. Thanks, Carlos.
Great. Thanks, Carlos. Enjoy the road trip.
Thanks. Bye.
Yeah, so to start to get a little bit more of a kind of detailed picture of what's going on with the graph geometry after applying these rules, we can start to think what's a better heuristic than just graph diameter. And one of the types of kind of measures that we have on a graph is this notion of dimension. So what is it? How do we define the dimension of a graph, right? What does that mean? And so, in the Wolfram physics project or in the Wolfram models, there's a fairly kind of well-defined way to compute dimension, and it comes from a very kind of geometrical intuition. So the idea is, if you start at one particular vertex in the graph, and then you find all the points that you can reach by traversing through one edge, right? Or all the points that you can reach traversing two edges or three edges and so on. In some sense, what you're constructing is kind of a ball. And so you can think of the number of vertices that can be reached by R edges is kind of like the volume of that ball. And so if you compute that for different values of R, different numbers of hops on the graph, then depending on the kind of dimension of the graph, you would expect that volume will grow, in a two-dimensional graph proportional to R squared or R cubed for a three-dimensional and so on. And in general, if you look at the, what is the volume of a d-dimensional ball just in normal space, it's obviously got a leading, it's obviously proportional to R to the D. And so from that, we can construct this dimension estimator, delta of R, where we look at essentially, that kind of ratio of success, the volume, the number of vertices within a radius R and R plus 1. And from that gives us a kind of estimator of dimension. This is, of course, for flat space. This estimator also actually gives us a little bit of a notion of curvature as well, because if you compute, this is the volume of a ball in flat d-dimensional space. If you compute what's the volume of a ball in a curved d-dimensional space, you still get this leading order R to the D term, but you also get an additional term that's of order R squared, where the constant of proportionality there is related to the curvature, specifically related to the Ricci scalar curvature. So from this estimator, what we would expect to see is this to be approximately, equal to the dimension, but then it's going to have an additional factor that's related to curvature as well. So we can actually, for the resulting graphs from our different rules, we can plot this estimator delta of R as a function of R. So here's what this looks like. So let's start with the plot in red. This is our input graph, unchanged, before any rule applications have taken place. And this is pretty typical of what these delta R plots look like. At very small values of R, very short ranges, you're going to get, that it's going to be dominated by kind of like, what is that microstructure of that graph? So it's going to be kind of, in some sense, noisy at very small values of R. And then as R increases, you'll get this kind of plateau where this estimator is kind of essentially kind of converges with the dimension, the value of D that you would expect. And then as you continue to grow that radius, eventually the ball is going to kind of hit the edge of the graph, right? Because we're looking at kind of small, finite kind of patches of the graph. It's going to hit the edge, and then that's going to cause the estimator to kind of drop down to 0 as well. So that's kind of what we see for this input graph. You see a lot better correspondence if you're able to do kind of a massive graph of thousands of vertices. But even on this one with just kind of 500 vertices, we see, kind of medium values of R, a plateau around 2, so around 2-dimensional, because we're taking this two spatial dimension slice as a Schwarzschild solution.
Wait, what's red?
And then
the red line?
The red is the input graph before we applied any rules.
Got it.
And so that's kind of what we want to match. If the geometry is unchanging, then we want, after we apply the rules, that the profile is kind of similar, right, to what it was to begin with. And so you can see kind of two pretty distinct behaviors coming out of this plot. So each of the blue lines now is one of those 719 rules, and you can see there's a kind of a subset of the rules that track pretty closely with that input graph, and then there's another set of rules that show a different kind of behavior. And can we understand what this behavior kind of corresponds to geometrically? So what we see is kind of like a peak, spiking up to a higher dimension, value, and then quickly dropping off, falling off a lot more rapidly than we had previously. And so both of this kind of point to essentially that graph is becoming very densely connected, so that, as you increase your radius, the number of points you can reach with a small radius becomes greater and greater, until you can eventually reach the entire graph with just a small number of hops. And so, these rules are kind of essentially just increasing the dimension of the graph very rapidly, and kind of shrinking the graph diameter is another way you can think about that. And so it turns out that it's actually a pretty easy kind of criteria that will allow us to filter according to these two behaviors. And so we can just look back at the graph diameter again, but previously we just used a threshold of 50% of the original value. But using this kind of plot, we can fine tune that threshold. And just for this particular input graph, it turns out that if you put a threshold of 13 on the graph diameter, then that basically kind of perfectly distinguishes between these two different categories of rules. The graph diameter is essentially kind of what is the final value of R on this, is another way of looking at it. And so with that, we're able to find, a subset of rules that match the geometry pretty well, both in terms of, dimension, but, if there are, the curvature effects are in some ways being accounted for in this kind of plot as well. And then so from that, we're left with just 32 candidate rules from the original space of 49,000. And here they all are. So you can see these are all 32 rules that made the cut, shown here together with the final state of the Schwarzschild graph after 5 iterations. And so, you can still see quite a range of different behaviors here. They all have the kind of features that we might hope to see, something that looks like the original kind of event horizon is still there. But you can see, different kinds of densities, different patterns, some that are showing kind of interesting kind of branching effects and so on. So this isn't to say that these rules will be good rules. You know, we can evolve them longer. We can try larger graphs. We can try different kinds of structures. But you know, I think it's quite interesting that from just a kind of very basic analysis, starting with a pretty large space, we're able to filter it down to a small number of candidates that could deserve further attention.
Were there any rules that of the 2-2 that remained? Because most of these here look like there's at least a 3-edge.
Yeah, I think they're the ones on the right-hand side here. Yeah, so these are some 2-2 rules that remained. I believe if you just visually, it looks like these. So there are 4 rules of 2-2 that remained, and it looks like, but it looks like really they're probably only 2 distinct ones, because these 2 look isomorphic. Just, I mean, that was, I didn't have to, I wanted to check that, you know, are they essentially the same rule? But
Looks like
Are they
it's
actually removing a vertex? Like it's like 3 vertices going in, 2 vertices going out.
yeah, this is where, you know, you have to be careful, right? It's a bit harder to reason about because I think you would think it would remove a vertex and that it would shrink the graph, but the graph does not shrink in size. And I think that's because of the way that the application works, that vertex that is in some sense removed may still be involved in other edges in the graph, right?
Oh, it's okay. Yes.
Yeah.
Yeah.
So it's things like this that.
Yeah, Wolfram Model rules, they don't actually remove vertices. Yeah, they just change the edges.
So it just becomes
Yeah.
disconnected potentially. So you could have a few loose vertices. Nick?
Well, they can be connected, but yeah, you just in the rule on the left hand side of the rule, you don't actually show all the context, right? It may be connected
Yes.
all up.
Yeah.
It's just in our hypergraph packet we don't. If they actually no vertex on the right hand side, we actually that actually means we remove it, right? I think Wolfram Model rule works a bit different.
I see.
Yeah, that's why it's a little bit hard to reason about because it is context dependent, and certain rules, again with a particular kind of choice of microstructure, they may well remove a vertex or end up in a disconnected single vertex. But in this case, it passed the disconnection criteria, right? So this has not resulted in any disconnected pieces. It just so happens that although the rule you know, kind of appears to remove a vertex, it still remains connected into the graph overall. So yeah, it's pretty interesting. I'm sure there's like a ton more we could learn about like why do these rules you know, behave the way that they do. I think this is really just kind of scratching the surface, but you know, essentially you know, where I think we kind of landed was you know, we applied a lot of simplifying assumptions to get here. You know, some of those assumptions were, you know, not necessarily selected according to the most rigorous kind of thought process. So it was really kind of what's the simplest thing that could possibly work. We may have overlooked or eliminated rules that are of interest. But I think the kind of my takeaway from this project was really that using this kind of methodology of doing a systematic search using heuristic criteria can be quite a powerful way to explore the space of rules. I was surprised, you know, that we were able to eliminate, you know, pretty large number of the rules. So the rules that passed these criteria were relatively rare, so 0.07% of the input set. But it wasn't 100%, right? So you know, there are still rules of interest remaining. And then I think kind of the biggest question mark is really how to think about this interplay between the microstructure of the graph and the rules themselves. You know, we don't really know what is the correct kind of vacuum microstructure of you know, of Wolfram models that have correspondence to physics. And so that's kind of definitely a challenge that deserves some more thought going forwards here. And there's just a ton of different ways that I would love to, or maybe others can look at to kind of extend this work in the future. It would definitely be great to look at what happens with larger graphs and longer evolutions. We're just so constrained on these small graphs. We want to obviously do the full three-dimensional solution to Schwarzschild and flat space. I think it would be interesting to look at other kinds of vacuum solutions, potentially things that involve shear. I think that's a kind of interesting kind of phenomenon that would be interesting to see how that maps into discrete space. And then using more sophisticated heuristics or non-vacuum conditions. And then kind of on this question of the interplay between the microstructure and the rules, I think, and that, potentially kind of in the direction that Carlos was mentioning, I think there's a lot, we could get a lot smarter about reasoning about the rules. And, maybe there are certain equivalencies between, transformations on the rules and transformations on the microstructure. For those that want some more information about this, so as part of the Wolfram Summer School, kind of what I would say the kind of main outcome is a write-up on the Wolfram community page. So, if you want to see kind of some more of the details, I posted this project there, and that QR code will take you through to that. And, obviously if you're want some more information about the summer school or the physics projects, those links are there.
Very cool. Thanks so much for that, Fergus. This was very productive in terms of actually getting to do some interesting outcomes. And what you mentioned there is like applying heuristics and exhaustive search to actually like figure some stuff out and almost more like build intuition, if nothing else. It kind of feels like that's what made other scientific fields very productive. And it kind of feels like that's what happens in machine learning sometimes. It's like there's not necessarily a scientifically rigorous theory as to why you've taken one route versus the other, but the outcomes kind of like validate the approach in hindsight. So this is very cool. A couple of questions. So right in the beginning, David asked a basic question: don't we expect gravity in GR to require curved, not flat spacetime?
So curvature is going to correspond to kind of gravitational effects, but a possible solution is also just there is no gravity, right? There's just empty space, flat space. So we can consider both. So certainly, the flat space solutions would not be, there's no gravity there, but the Schwarzschild black hole solution is obviously very curved and does show gravity.
Okay, then there was just some questions there around growth of spheres versus balls, but I think that was kind of the difference there. Because the comment was the larger the sphere, the lower the dimensionality because of lower curvature. But I guess this is not a sphere, it's more like density, something like that. Like a sphere wouldn't have, like, yeah, does it make sense?
Yeah, I'm not totally sure I understand the question, but yeah, essentially, the procedure is looking at kind of the volume of balls. I say volume, but in the case of a two-dimensional graph, that would be area, or higher than 3 dimensions, and kind of hypervolume. But we can use that as an estimator for the dimension, and that's going to be that kind of strong leading order term r to the d, right? Which is going to kind of dominate that volume. But yeah, as the question points out, you do need to apply a correction for that in curve space that's going to be proportional to the scalar curvature.
There's also a comment here that says that maybe considering uniformity of the graph would be an interesting heuristic.
Yeah, definitely. Yeah, I mean, I was thinking about, like, could you also start to look at, does the rule change? Essentially, you can kind of look at neighborhoods in the graph, right? You can look at kind of individual vertices and what does the structure look like around, in a distance, say, one hop away from that vertex, and kind of get a sense of the neighborhoods, and maybe do some statistics on those neighborhoods, right? Look at the entropy or the distribution of different neighborhoods, and see, does the rule change that in some way? Yeah, I think that would be a really, really cool thing to look at. But yeah, I wasn't able to do anything in that regard.
Can you go to the graph? I had a question. Can you go to the graph with that showed the curves over time, then you're trying to match it, the output to the input here?
This one, yeah.
Yeah, so this was actually really interesting, and it was making me think of how this kind of the bulk of the rules would shift if you changed some of the rules that you would search over, or maybe some of the heuristics. And the interesting thing for me was if you had rules that created like an expanding graph, how that could potentially shift this graph to maybe have more rules that would match something.
Yeah. I think the criteria that the graph should not grow is, it's definitely somewhat, it's fairly restrictive, which is good in terms of cutting down the search space, but it may be too restrictive. Stephen, for example, has suggested that you could have there are rules that essentially appear to do subdivision. So if you have an initial graph, then it will kind of almost kind of subdivide it in some way, and keep this kind of similar structure, but kind of continue to subdivide. And you could imagine that even though the number of vertices in that graph is changing, is increasing exponentially, could you kind of still say that it's physical if you if the distance between 2 points, you kind of have to, it makes it a lot more complicated because you have to think about how the metric is changing over time, but you could think of it as a kind of subdividing rather than necessarily growing kind of process. So yeah, you could definitely imagine making a more complex model where you'd have to change the metric, but the graph metric I'm talking about in this case.
So it would maybe be like a proportional metric instead of a unit metric or something like that.
Yeah. I guess what I mean by that is, we're defining distance as just the number of, the smallest number of edges between 2 points. But, and so by that measure, all distances, in those graphs that subdivide, all distances will appear to get longer kind of at every time step, which is not what we observe in the real world.
Well, that's what I wanted to ask about.
A more complicated scheme, yeah.
Well, I mean, that's what I wanted to ask about, because wouldn't a conceptualization of the universe expanding kind of be similar to that? Because the comment "not physical" was interesting there, because you could say that everything's expanding all the time. So the actual measure is only in the fact that it's it's proportional.
Yeah,
all the time.
I think that is an interesting kind of constraint, because we do observe lengths growing, right? So but they grow very, very slowly, right, compared to these kind of like an exponential growth process that you would see in a graph. So it is a question, and that's actually kind of partly what I was thinking about. Your initial comment, Nick, around multiple different rules, right? We've restricted the rules to show no growth, but maybe we need rules that show some growth, but just very, very, very slow growth, right? And it's hard to get that. It's hard to get that kind of behavior from a single rule. So I think that thinking about that could be a very interesting constraint, but whether or not that's necessary, but I think it's a very interesting line of thought.
Very cool.
And I believe there has been some work done on the kind of the cosmology of Wolfram models, but I'm not familiar with that. Like,
any questions,
Okay.
comments from Dugan or Nick? Oh, David's actually just popped a comment in here. So he does a lot of general relativity stuff. The universe and the lengths of meters are expanding, arguably a core tenet of Einstein's curvature theory.
Yeah.
Cool.
Yeah, but if you imagine the time scale of one single update is got to be, you know, very, very, very short, right? And if that, you know, if every kind of single epoch of time results in a, you know, multiplicative factor on all lengths, I just think that would be, it's hard to imagine that would result in the kind of, you know, fairly slow growth that we see.
I just had a few questions on this plot.
Sure.
Is this drawing dimensionality from a Schwarzschild solution, or is this a two-dimensional graph?
Yeah, it's a two-dimensional slice. It's a two-dimensional spatial slice through Schwarzschild solution. Yeah, so in red,
Well, like if you go back one slide, is this a forward one?
Yeah.
Is this where you're making the R plots, the dimensionality plots as radius increases? Like you start in the middle here, and then you get like these balls and you measure them.
Yeah, so that this is how I'm computing delta of R. But in the case here, this red line corresponds to doing that procedure on exactly this initial condition, the Schwarzschild graph. And yeah, the question is like, what is the center point? So I just used the graph center. So the point that I forget the exact definition, you know, but essentially you can you know, there's ways to find a kind of central point. It's the point that's kind of most distant from all other points, essentially. As a starting point, again, pretty arbitrary. And then I actually do then take a neighborhood of points around that graph center and average delta of R across. I believe I used a neighborhood of one. No, it was more than that. It was a couple of hops essentially. So it ends up averaging over a number of different kind of starting initial vertices. Because this, you know, it is a very noisy estimator, and it's kind of a good question. Are there better things we could be doing here? But yeah, so that's actually where those error bars come from. That's kind of the range of different values you get from averaging, or from kind of looking at different initial center vertices of the ball in a small neighborhood. So that's the one in red, and then in blue. So red is the initial condition, so just the pure slice of the Schwarzschild solution, and then the blue ones are the ones after the rule application.
And I guess the graph center, the starting vertex where you're centering these balls, is changing each time at each plot.
Yes, yeah, I did. I recomputed the graph center for each kind of final condition, because it's a little bit hard to keep track of what does it mean for a vertex to even stay the same after the rule application, right? Yeah.
Okay, that's all my questions. Very interesting work.
Cool. Nick, any closing thoughts?
So I have like a question. Maybe I don't know whether you thought about it, like how much it is like. All the criteria that you tried essentially was about the structure of the graph, right? Like the space-time itself. But there's also an actual matter, right, in the universe and the Einstein equations. So what kind of criteria you can base, like some energy conservation, and how can you look for those, right?
Yeah.
Maybe also filter out.
Yeah, then you get into dynamics as well, right? Because then you will expect yeah, the kind of key, like the main simplification, right, is if we look at static solution, then we just need to check that the input and the output is the same, right? In some sense, the rule doesn't change the structure. If we introduce, more complex solutions that potentially have dynamic behavior, you need to go smarter about, your initial and final conditions may be different.
Have you got any ideas of how you would measure that? And what are those solutions called? So you have the static solutions, then what is the other dynamic solutions?
The dynamic solution. Yeah.
Have you got any idea of how you would?
It gets tricky. I mean, the other like sleight that maybe you can call it sleight of hand here is like, the question of whether it's even proper to consider just spatial slices, right? We're not considering full space-time at all. These are all just essentially spatial slices. And, that was the intuition behind kind of why that's okay is around, the fact that it is a static solution. But that's definitely something which could require a bit more rigor to kind of say that this is a reasonable thing to do. But then if you get into dynamic solutions, then that's probably not okay anymore. And you need to think about, just a little bit more sophisticated way of how you think about the evolution.
Is it possible, I think, like you impose your structure, right, from the equation, like the Schwarzschild solution? Is that how you initially sample your initial graph, right? So you kind of know the mass of the black hole or whatever, right? But can you estimate back, like after you evolve the graph a little bit? Can you actually estimate the graph from the graph, this mass from the graph structure? I think like
that. Yes. Yeah.
So that you can.
Yeah, I mean, in theory, that's encoded in the curvature, right? So if you can measure the curvature, you might be able to back that out. Yeah, that would be very interesting to look at.
Well, isn't that basically what's happening here? It's like the kind of the mass of the black hole staying the same in theoretically if that band is the same as it was. Could you say that, or was that a leap?
Yeah, I mean, certainly if the mass was, I don't know. I think it's pointing in that direction, but this plot is obviously like kind of averaging over a lot of different effects, right? So, yeah, I think it would be a good direction to kind of look at the individual kind of components of curvature, or look at sectional curvature, to get a more, because this volume measure is only sensitive to scalar curvature.
Okay.
So, yeah. So you're kind of, you've averaged out, you're kind of tracing the curvature, but you might, there are people come up with procedures to measure the individual kind of components of curvature. But that could be interesting to look at also.
Yeah. Well, ultimately, it's like you have to actually find a rule that matches the actual evolution. So if you had like many computational resources, you'll actually like compute all the slices of the actual evolution of the Einstein equation, and then you compare it to all the rules and how closely they match, and that would be like the ultimate test.
What do you think? What do you think the number of CPUs you would need to run simultaneously to get that working? Like 1,000 H100s or like 10,000 H100s?
Well, we already managed to filter out. We have a good selection. Like that's why the heuristics are useful. You don't have to try all of them to actually try this complicated comparison. Now we have 32 rules, at least of this particular signature, to just compare it, how bad it is from the actual.
And it seems it's really sensitive to the number of vertices. So the small input graph with about 200 vertices could search the full space of 50,000 rules on my laptop in about 20 minutes. But going to 500 vertices, the Schwarzschild solution, it took about 8 hours and 70 gigs of RAM to search the full space, and then actually crashed before writing the result to disk. So I
Oh,
wasn't
no.
able to do the full 50,000.
So it finished searching, but it didn't save.
Yeah, for one particular case. Yeah, so it's very sensitive. I don't know what the actual kind of what the asymptotics are, but it's very sensitive to the number of vertices.
Very cool. Okay, thanks so much. That was a awesome presentation. And yeah, we look forward to future work in this direction. I think the concepts here are useful. You know, doing a proper exploration of the Ruliad space and taking that concept to heart definitely made for some interesting presentations. So I appreciate your time. Thanks for the guests for joining, and thanks Fergus so much for doing the project and joining us today.